Hello everyone, I am Monika Bhushan and today we are starting lecture number 12 of partial differential equation. So since last two classes we are seeing the solution of Lagrange's partial differential equation, right? So last classes, that means lecture number 10, we had seen the solution of Lagrange's partial differential equation by grouping method. Last class we covered solution of Lagrange's partial differential equation by method of multiplier, and today's class we are going to see the combination method to solve the Lagrange's partial differential equation. That means in one question only we are going to take help of grouping method as well as method of multiplier. So which type of question actually will be there, so that we need to use these two methods that we are going to see. Fine. Okay, so we will be working on this question. So the question is solve x square minus y square minus z square p plus 2xyq minus 2xz equals 0. So very first thing, since we are seeing in two classes, that first thing we have to actually understand that this comes under Lagrange's form of partial differential equation. So since I assume that you know all these things, whatever we have discussed. So we understood that, yeah, this is the Lagrange's PDE. So we will be working on the solution, which will be always first we will try with grouping method, and then if it is not working, then we will move for method of multiplier. And in this question, actually, not a single method will be enough. We are going to take help of both methods. Fine. So the method is exactly same. What method we are discussing since two classes? That means the step number one is what? Step number one is to notice that what is my capital P, what is my capital Q, and what is my capital R. These P, Q, R are nothing but the functions with respect to x, y, z. So we got these three things. Fine, no? So we got what is my P, Q and R. So this is minus 2xz equals 0. So what we are writing down? We are taking this 2xz into right hand side, because my Lagrange's form says that this is my capital P, P plus capital Q, Q equals R. So I'm just taking right hand side the term where I don't have P, where I don't have Q. Fine, no? So the term which is free of PQ, I'm just taking into the right hand side. And so this is positive 2xz. Fine. Now, what is my step number 2? So here also step number 2 is only somewhere we have to start working on different methods, because we know that step number 3 is nothing but my integration method, right? So we are going to just integrate in my step number 3, and finally we will get the solution. What will be solution? Solution will be in the form of phi u comma v equals 0. Fine. And these u v only we are going to get in my step number 2. Okay. So step number 2 starts with writing down Lagrange's auxiliary equation or Lagrange's subsidiary equation. Fine. So this is our Lagrange's auxiliary equation which we have written down. So the system of equations we have actually written down with respect to our capital P, capital Q and capital R. So I think till here we don't have any doubt, because we are seeing so many questions till now we have seen in last classes. So after that, after this step, what we have to do? So since we are going to always start with method of grouping, the reason because it will take lesser time in exam, and it is by scanning the equation only we can understand that whether the grouping will work or not work. Suppose we are just starting with grouping method. We are just trying to group this first fraction and the second fraction. So here we see that the first fraction is with respect to dx, second fraction is with respect to dy. So in this case, what we should be having? We should not have z present, because if z will be present, so we will not be able to integrate. That means we will be getting the trouble in step number 3. Fine. So these two grouping will not work, because we have z and z we cannot cancel out, and z cannot be integrated in these two set of fractions. Suppose I'm trying the grouping between second and third. Fine. So fraction 2 and fraction 3, I'm just trying to have the grouping. So in that case, what we should have? So we should not have x present, because this is the first fraction is with respect to y, the second fraction is with respect to z. So x should not be there, and if x is there, so it should get cancelled. So fine, I can see the presence of x, but x can be cancelled out. So I will be having dy with respect to y, dz with respect to z in these two fractions. So the grouping between 2 and 3 will work. Fine. I am able to get by grouping the second and third fraction. Right. So what we have written down here, so considering last two fractions, so these two fractions since we have considered, and this 2 also gets cancelled. So finally we got dy by y equals dz by z. Fine. So I can write here the simplified form. I can write here. So here my step number 2 is done. Fine. So what is my step number 3? I have to integrate, right? No, the left hand side and right hand side, both sides I am going to integrate. And why I am integrating? Because I need to have the constants C1 and C2. So the arbitrary constant I will be getting in my step number 3, that I will equate with u and later on with v also. Fine. So we know that integration of dy by y will give me log y. Okay. And then right hand side will be what? Integration of dz by z will give me log z. Okay. And then plus c. So arbitrary constant here I am not adding. I am adding in the right hand side only. So I am writing down the name as c1. So I can write that log y minus log z equals c1. And if I will write instead of c1, if I will write log c1, that also will be fine. Right? The reason is exactly same what we keep on discussing, because I want to make the equation in simplified form. C1 is some arbitrary constant, and log C1 will also be some arbitrary constant. So taking log of C1 will not violate the nature of C1. Fine. So what we are saying here, so the left hand side will be log y minus log z is nothing but log y by z. We know this formula, correct? And then right hand side I am writing down log C1, so that if I take anti-log both sides, so log will go off. So my C1 will be what? Y by z. And this C1 only I am going to equate with u. So I am going to say that u is y by z. And what is u? So u is one of those two independent solutions, right? So u is my y by z. So we got one solution. Now I am working on, now I have to work on what is my v. Fine. So to get v, again I'll try the grouping between first and third. So if grouping between first and third will work, then that will be fine. So now we'll see that the first will not actually have grouping with even third also, because here only the first one, it is with respect to x only. I mean the dx is present, but my denominator has x, y, z, everything. Fine. So now what we are going to say, that now this is also not working. This has worked. So now we are going to take help of method of multiplier. So in method of multiplier, remember what we used to do? For method of multiplier, we are going to choose three different multipliers, right? So if I am taking the name of multipliers as LMN, so these three LMN can be any constant. These three LMN can be any function of XYZ, and these can be same or different. There won't be any problem in that. Okay, so these three multipliers will be useful to have one more fractional term, correct? So the next new fractional term will be what? We are going to arrange the multipliers such a way that the numerator of the fraction will be what? It will be L dx plus M dy plus N dz, and the denominator of the new fraction will be what? It will be my L capital P plus M capital Q plus N capital R. And then these four fractions are actually same, because we are going to choose the multipliers in such a way that this fractional term will also be same to these remaining terms. So we'll just give some name as K. Fine. So in that case, in last class, we had said that we are going to work on this denominator, that if this LP plus MQ plus NR will be 0, so it will be good for us. That means the third step will be much easier, because what we had said, that if I'm going to write this, if I'm focusing on these two things, that means L dx plus M dy plus N dz will give me how much? K into Lp plus Mq plus Nr. Fine. So these things we had said. Suppose this Lp plus Mq plus Nr will be 0. So in that case, it will be L dx plus M dy plus N dz equals 0. And in that case, the integration part will be easier. Fine. So now we will be seeing that can we use this in the same fashion, or there will be some difference. So fine. So what we are going to now start with, we are going to now start taking some three multipliers LMN. So what multiplier we can choose, because this L will be actually multiplied in the first term's numerator and denominator. Fine, because I have to write down in this fashion, and then this M will be multiplied to the second term, and then N will be multiplied to the third term. Fine. We can think that here the first term has square, right? X square, y square, z square. The second term has just x, y. The third term has just x, z. And we can see even the second term contains x. Third term also, the third fraction also contains x. The first fraction also contains x, but it is x square. Fine. So if I will multiply y in my second fractional term and z in my third fractional term, so what will happen? Then it will be something like 2xy square, and then it will be 2xz square, the denominator of second fraction and the third fraction. So this will be how this will be useful, because we can see that y square term we have got, z square term we have got, and suppose x in my first term. So what will happen? Then I will see that this x will be common, right? And then if I take these three common, and if I take these 3x common from each and every fractional term, so everything will be in the square form, right? It will be x if I have taken now, so it will be x square only, so x square, and it will be y square, z square kind of thing. So we have to actually try in by applying some trick, so that we will get the correct multipliers. Okay, the working multiplier. Okay, so if suppose I am choosing LMN as x y z. Fine. So what will happen? So in that case it will be, so in that case my LP plus MQ plus NR will be how much? So it will be my x into P is what? P is x square minus y square minus z square, right now, because this is my P. So what will be my M into Q? M, I have said that this is y. So M into Q. Q is 2xy. So it will be your 2xy square, fine, plus N into R, correct? No. So N into R will give you how much? It will give me 2xz square. So 2xz square. And this will give me what? It is, if I am taking x common from each and every term, right? Here only I am taking x common. So now it is your x square minus y square minus z square plus 2y square plus 2z square. Okay, and then it is nothing but x into it is your x square, then 2y square minus y square will give you plus y square, and then similarly plus 2z square minus z square will give you plus z square. Okay, x square plus y square plus z square will not be 0, they are the positive terms, and here I cannot see x is 0. So this is the advantage of combination method, because this combination method allows us at any step to either switch grouping method or to method of multiplier. So we will be actually now taking help of grouping method. So we'll see that what I am saying here, till here we got fine, this is okay. Now we have chosen x y z as multiplier, and then we are equating it with k, fine. And now we have said that fine, so till here we also have got the this step we also have reached, fine. No, because the denominator is x into x square plus y square plus z square, and what was our numerator? X dx plus y dy plus z dz, this equals k. Fine. So after this step now, we will go back and check the other fractions so that can we actually do the grouping with this new fractional term. So the previous three fractional terms and this fractional term can be grouped or not. Fine. Okay, fine. So we can see that this is the second fraction and this is the new fraction. So these two fractions can actually make the grouping. And how they can make the grouping? Because the second fraction was my dy by 2xy and this is the fourth fractional term which we have got. So if I will try to make grouping between this second and the new, that is the fourth fraction, so I can say that the first fraction is with respect to y, okay, and the second fraction has even dx, dy, dz all are there. So in my first fraction, if other than y, if any other independent variable or any variable is present, so it will be difficult for me to integrate. So we can see that x is present. Fine. This x I can cancel out. Fine. So now it will be your dy by y. So this 2 we have taken into the right hand side, and now this is your x dx plus y dy plus z dz by x square plus y square plus z square. So here we don't have any problem. The reason, because I can actually have x, y, z all variables present, because this fraction contains dx also, dy also, dz also, and now this fraction is having dy, so only y independent variable is present. So so there won't be any problem in the integration term. That means the step number 3 will be now easier. Similarly, you could have done the grouping between your third fraction and then this new fraction. Fine, because there also we had 2xz, so x will get cancelled and then z will be there, so both things will be actually same. Okay, so now we are done with our step number 2. Why? Because now we can say that we can actually find out what is my v, because now I will be able to integrate these two fractions. Fine. So my step number 3 says what? We have to do the integration in left hand side also and then right hand side also. So writing down integral of dy by y equals my integration of 2x dx plus 2y dy plus 2z dz divided by x square plus y square plus z square. Okay. So now this is your dy by y, integration of dy by y will give you how much? Log y. Okay. Now what about my right hand side? How I am going to find the integration here? So for that I'll just substitute as t, right? T is your x square plus y square plus z square. So what will be your dt? So dt will be your, it will be your 2x dx, fine, plus 2y dy plus 2z dz. Is that okay to say? So in that case, I can say that here, if I see my integration, so 2x dx plus 2y dy plus 2z dz is nothing but dt. So I am writing down dt, and then this we have assumed this is nothing but t. Okay, so that means my left hand side is log y and then right hand side is how much? Log t plus c2, because c1 we have already used. Okay, so this is what? This is log y equals log t is how much? X square plus y square plus z square plus c2. Now the same concept, c2 is any arbitrary constant, the value I don't know. So instead of c2 I can write log c2. Writing down log c2, so the reason of writing down log c2 is to make the equation simplified form, and even log c2 is again going to give me some another arbitrary constant, right? So it is also some arbitrary constant, fine, and c2 was also some arbitrary constant. So I'm not making any difference in the nature of this this additional arbitrary constant, fine. So what I'm writing down here, log y minus log x square plus y square plus z square equals log c2, fine. So left hand side will be what? Log a minus log b is nothing but log a by b. So y by x square plus y square plus z square, and then this is nothing but log c2. So taking anti-log both sides, it will be nothing but c2 is nothing but c2 is your y by x square plus y square plus z square, and C2 only I am writing as my v, the other solution. So v is y by x square plus y square plus z square. Fine. So we have got here also. So finally the solution is phi u comma v equals 0. That means phi y by z, which was my u, and then v, which is my y by x square plus y square plus z square equals 0, is the required solution. So in this question we have seen that we have actually solved this question with the help of grouping method also and my method of multiplier also. So this was the combination method. Okay. So if you find this class useful, please like and subscribe my channel. Thank you.